Next up, we have Jugal and Holly going to be talking to us about hardening machine learning against adversarial attacks. Jugal and Holly both join us also from the Windows Defender research team. Jugal has been working in the field of security and machine learning for 7 years. He enjoys solving complex security problems like targeted attacks, using static and behavioral file script-based detections, detecting adversarial attacks using machine learning, and he's currently a senior data scientist. Holly has been in the security industry since 1997 in many different types of disciplines, including product and program management, incident response, communications, and for the past few years, data science. She's a principal research manager for the Defender antivirus research team. And please give him a big round of applause. I'm excited for your talk. Thanks.
Thanks. Hi. All right. So I want to open up with a typical day in the life for us. So this shows you an average day in the middle of May. And on that day, we had 2.6 million people get hit in 232 countries around the world with 1.7 million attacks that we had never witnessed before. Brand new, first seen attacks. What's worse is that 60% of these attacks, they were over within the hour. So in the security field, we think a lot about response and response time. But we're getting to a place where response doesn't matter. So we serve about 500 million customers. They are counting on us every single day to get this right, to be able to predict that 1.2 million attacks were malicious and stop them at first sight. And there's plenty of folks out there who want us to get this wrong, right? They want to defraud these folks. They want to make their millions off of these people. And it's up to us to keep them safe. So in this world where response time doesn't really cut it anymore, we've turned to machine learning, to AI, for this promise of the predictive power, the promise to be able to stop it at first sight. But just like people are susceptible to social engineering, well, machine learning has its flaws too, and it's susceptible to adversarial attacks and to tampering. So I'm Holly, and this is Jugal. Randy is probably watching the live stream right now. And we are part of the Windows Defender research team. And similar to if you were here for the previous talk, we're all on the same team. And this is what keeps us up at night, is keeping these people safe from these first seen attacks. So our particular team is called the Threat Predict Research Team. And our primary focus is using machine learning to predict threats. I know that there are probably some machine learning experts in the crowd right now, but to make sure that we're all on the same page, I want to go through a quick primer. There are two primary types of machine learning that we use in Windows Defender. The first is called supervised machine learning. With supervised machine learning, you have experts who label samples, either behaviors or malicious files or combinations of those things. They create labels to help us distinguish malware from clean. Then we take those labeled samples and we submit them to a machine learning learner. And that machine learning system learns on those examples and then creates a model that can predict malicious and clean for future samples. So this is supervised machine learning. There's also unsupervised machine learning. So unsupervised machine learning does not have labels to tell you what is good and bad. And it's great at uncovering the blind spots that your experts may have. It's really great at doing things like clustering similar things together. So you may be able to surface new pockets of malicious files or malicious activity that you haven't spotted before. You might be able to find new types of clean files that you haven't classified yet. It's also great at looking for anomalies, so you can use anomaly detection to look for spikes, which can sometimes indicate that bad things are happening as well. Today, we're going to be focusing on adversarial attacks against supervised machine learning. Machine learning can be employed at multiple levels when you're talking about endpoint protection. If you were here for Jeff's talk, he walked through some of this a little bit. You can employ it at the client. You can employ it at the cloud. These are the two major areas where you can use machine learning. On the client side, you want those machine learning models to be super fast. Client-based detection is really great for things that are obvious when you're looking at the blocking perspective. Because let's say a malicious attacker is using some type of clearly malicious behavior, those things are easy to block at the client because the attacker can't really hide that. It's also really good for commodity malware. So if you've got kind of some simple malware that isn't doing a whole lot of obfuscation to try and evade detection, pretty good to detect at the client, especially if it's high volume. It's probably more efficient to do at the client level. For the more sophisticated attacks, we tend to move to the cloud-based models because they're more difficult to evade, and we can see people testing us when they check our cloud-based detection system. So there are multiple layers within our cloud that we use for protection. The first is the metadata-based layer. So when that client examines behaviors or files, and if it's not quite sure whether that's clean or malicious behavior, it will send those signals up to cloud. And when I say signals, I mean hundreds of thousands of attributes that are related to that activity. And our cloud-based models will take those hundreds of thousands of attributes. We've got multiple models that run at this layer, and provide their predictions within milliseconds, send that back down to the client, and the client will protect the user from that bad behavior or those bad files. If our cloud-based models don't have an answer, then sometimes we will ask for a sample of the activity, and we'll upload that to our cloud-based system. Now, the way this works is the metadata-based layers say, this activity looks a little suspicious. Hey, client, put a hold on that file. Don't let it run. Send it to me so I can do a little more analysis on this. So we upload the file. Some additional properties are extracted, things that would be a little too heavyweight for the client. And then we run a deep learning model, which is much more intensive, to get a much more accurate response back down to the client. So the client says, OK, I'll hold it for about 20 seconds. You better get the answer back to me really quickly. So it'll hold for about 20 seconds, and the sample-based model will send the response down, tell it to either block that file or let it go because it's clean. So these are our real-time protection layers. We've got a few other layers that happen in cloud, detonation-based models. Of course, it takes minutes to detonate a file in a VM, and you're not always guaranteed that the file is going to show us malicious behaviors when it's in a VM, so they have these anti-emulation tricks that they like to do. And then we have metadata-based models, big data-based models that correlate signals from many different places, Office 365 and many other components that we're incorporating into our cloud-based system, but sometimes this can take a couple of hours and isn't great for real-time protection. So most of the protection we do are at the quick layers at the very top of the funnel that you see. And today we're going to focus on adversarial attacks against the first two, primarily the metadata-based models. So there's a couple of pros and cons about using machine learning at the client versus cloud. And this is really important when you're thinking about adversarial attacks here, because one thing that we have seen is that when it comes to client-based protection, if you put all of your protection capabilities there, well, an attacker can take your client, take it offline, test it forever, essentially find out what the answers are to the test, right? They know what you detect is clean, they know what you miss is malware, and then they can use that knowledge and go attack people in the real world without you ever having seen that they have done this testing, right? That's the disadvantage of client-based systems. Now, if you've got an environment where you have disconnected clients, or maybe they're not talking to cloud for whatever reason, yeah, it's great to have protection where you don't have to talk to cloud, but with adversarial attacks, it's a true disadvantage. On the cloud side, if you're requiring the attacker to talk to your cloud, they can't do this private brute forcing. to test your protection, they have to talk to you. And that means that you can see them. And that means that you can figure out what to do in response to that. Maybe you change the answers up a little bit. Or maybe you provide some other controls that prevent that attacker from being able to thwart your protection capabilities. The other benefit is that there is minimal client impact. So we put a lot of our heavy-duty models in the cloud because you can have lots of compute power in cloud. And that means that the client can be super lightweight, no experience interruptions to the end user, right? Put that power in the cloud, put those deep learning models up there. All right, so I want to walk you through some theoretical attack vectors for a machine learning pipeline. And most of these vectors require some insider knowledge, so keep that in mind as I talk about them. At the first level of the pipeline, you have your sample set, your clean and your malicious sample set. So if an attacker can get access to that, they can completely change the ratio of clean to malware that you're using to train your models. They could flip labels, give you labels that are malware that are now labeled as clean. And this can be catastrophic to a model because a lot of folks, I don't know how many of you out there build machine learning models, but I know we all tend to kind of focus on what learner should I use? You know, there's 20 different models I can try. There's a bunch of parameters that I can tweak. You know, there's all of these facets when you're creating your machine learning model. But the sample set often will have a much more powerful effect on how effective your model is than, you know, the particular model you're using and the parameter tweaks you do. So the sample set's really critical. So if an attacker gets access to your sample set and they can change what your model's training on, that can have catastrophic effects. The other thing that they can do is they can mess with your features. So if they know what features are important to your model, they can submit samples that trick your model into learning on the wrong features. And most of the papers that you'll see on adversarial ML focus on this. They will talk about adversarial examples. It's doing exactly that. They're taking examples, they're tweaking them, and they're flipping the decisions in your model. And Jugal will show some examples of that when he walks through the testing that he did for our cloud-based systems. The second thing they could do, if they know what model you're using and what parameters you're using, and they know your samples and your features, well, they could just basically take all of that offline and build the same model you've got and figure out how they can game your system, right? It's essentially the same as testing a client offline. Last but not least, let's say they really don't have access to any of these things, but they have kind of a guess at what samples you're using. Maybe they go to VirusTotal and they collect a bunch of clean and malicious samples, and they've got a guess about what features might be important. There are some new methods of black box interpretability that they may be able to use to figure out what features are important to you and then build samples that do feature evasion that can escape your model's results. Okay, so let's talk about some stuff that has actually happened in the wild. That was a whole bunch of theory. This is stuff that we've seen, okay? So this first example was actually an attack on our automation systems a couple of years ago, but essentially the same methodology could have affected our machine learning systems. What these attackers did is they tested our client offline, and it wasn't just our client. Actually, this happened to the whole AV industry. There were many other vendors who were victims of this attack. So these attackers tested these clients, and they learned what strings these clients were keying on to determine that something was malicious. So imagine you've got a binary. That binary connects to a malicious IP, and you know some part of that malicious IP is a component, a string that the AV system is using to determine that that is malicious. They took that knowledge, and then they looked at the way that we were automatically detecting files that were malicious. So just because that string was the indicator that something malicious isn't necessarily the thing the AV product will use to detect that file. That's what was happening in this case. So they learned not only the string that we were keying off of, but the way that we were detecting the files. So they used that knowledge. They took a clean file. They injected that malicious string into the clean file. left the header of the clean file, which was the part we were detecting on, intact, and then uploaded that file to VirusTotal in an anonymous way. Many vendors, including us, use VirusTotal to collect samples. And when these samples got processed through all of these vendors' automation systems, they ended up detecting these files. And the file itself is just specially crafted junk file. But when the detection logic kicked in, it happened on the header part of the file, the clean part of the file, which in the end result was it was detecting these clean files in the wild. Caused a major FP issue for us and a lot of other vendors. The second attack was on our cloud-based system. So this was an attack that tried to trick our certificate-based reputation system into trusting signed files that we shouldn't trust. And this attack was, these attackers were a little sloppy. They were sending in a whole lot of telemetry, a lot of traffic stuffing is what we call it. And it was so loud that it showed up immediately in our telemetry. We saw this as a very large percentage of traffic that was unclassified. And so, we saw it and started investigating it. We found that it wasn't just on these high volume attacks. There were a lot of low volume attacks that were using this technique as well, and also some unsigned files that were getting through the process. So how did they guess this? Well, reputation systems have pretty simple features. They look at time, they look at traffic, they look at the certificate, right? It's kind of easy to guess what the features were of this model. And they did. They guessed it, and they tried, tricking the systems. So what we did, and this was really a precursor to what we're going to talk about in depth today, the Ensemble approach, is we took another model to classify the attackers. And once we classified the attackers and separated them from our trusted telemetry base, then we were able to filter out this traffic from our training and prevent this from happening. So it's really just a combination of two models that end up with a better result. There was a lot of research, in fact. As some of you may know, Jay Stokes from MSR and others who have published a lot of research on using an ensemble approach to make your models less susceptible to tampering, less susceptible to attacks. Jugal is going to walk you through the experimentation we did and the testing we did and the final ensemble model that we came up with to help make our models more resilient to attacks.
All right. Oh. Thanks, Holly. All right. A quick show of hands. How many of you folks here know what model stacking or stacked ensembling is? OK. I see roughly 6 to 8 hands. And how many of you have actually used this technique to catch real-world threats? One, right there. Congratulations, sir. All right. By the time we are done with this presentation, I hope everyone here in this room understands this technique in details, learns the benefits of it, and hopefully try to reproduce this using your own data. OK, so stacking is an ensemble technique that combines the strength of several base learners. The base learners are trained using the entire training data. You then use the predictions from these base learners as inputs to train the stack classifier. The output of the stack classifier is then used as the final verdict. As some of you may be aware of, this is a very commonly used technique to gain that extra edge in machine learning competitions like Kaggle. But what happens when we use this technique and use it to catch real-world threats using our data? That comes with its own set of challenges. Some of you might be already aware of those. We actively deal with adversarial attempts, where the adversary is constantly trying to either evade their attack techniques or attack our detection methods directly. We see volatile data distribution, where our daily telemetry distribution is highly volatile. The distribution patterns that we see today might not be applicable for the telemetry we see tomorrow. Noisy environment, where sometimes we have to deal with noisy features, noisy labels. How does this technique compare there? How well does it scale when we use petabytes of threat intelligence daily to train this model? Let's go over some building blocks of this technique which is now used in our production environment to evaluate roughly 2.3 billion global queries every day. So diversity plays a very important role in generating not just an effective stack classifier, but also to ensure that the stack classifier is robust to adversarial attacks. This diversity can be achieved through different techniques. Let's go over each one of them in detail. The first one is different feature sets. Luckily for us, the field that we work in already has a very highly dimensional data set. Let me show you what kind of features we use. We use the machine attributes like OS information, the security settings of a potentially infected machine. We look at static attributes like fuzzy and partial hashes, along with file properties like file metadata, file geometry, and so on. We combine this with behavioral and contextual attributes like what sort of events the file generated, what's the child-parent relationship, what sort of network activity did it have. We also use custom features that are set by our researchers to extract more interesting properties from files, processes, and so on. As you can see, sky is the limit. We try to ensure that all these features are updated multiple times a day. A second way to achieve diversity in our base classifiers is by trying out different training algorithms and different training data sets. Depending on the type of data set and the total number of instances you have in that data set, it's highly likely that one set of learners perform better as compared to the others. If you look at the top 4 classifiers in this table, you'll see that an ensemble approach like boosted trees or back trees perform better when we look at static attributes or behavioral attributes. This works well when we have anywhere from 512 features all the way to 6 million features. When we increase our feature sets to, say, 10 million to 16 million features, a linear classifier performs better, like average perceptron and SDCA. Whereas for data like file emulation or file determination, we see that DNNs, or deep neural networks, work the best. You can further have diversity in these classifiers based on where these classifiers are meant to be deployed. You could have classifiers on the client, on the cloud, classifiers that work on the full file content, and so on. From a training data set perspective, one of the very easier ways to do it is by splitting your data set based on the file type. You could do PE versus non-PE file types, or further break it down to JavaScript, macro, VBS, and so on. Another thing you could do is train different classifiers and optimize them on different settings based on what sort of threat scenario they are trying to handle. One of the things that you could do is vary your training cadence. As Jeff mentioned in the previous presentation, 96% of the files, of the malware files, are only seen once on a machine. We have got to get it right the first time. If not, we leave the customer vulnerable to an attack. So we need classifiers that train multiple times a day or trains at least every day, and the classifiers are more sensitive to the incoming data telemetry. They are, in a way, overfit to your data distribution changes rapidly. Perhaps you want something that is focused on preventing regressions. In that case, you want a classifier that looks at older malware as well. In that case, it makes sense to train the classifier once every week or once every month or so on. Moreover, you could have classifiers that focus on different kinds of classes, not just a malware classifier, but a classifier that exclusively looks at clean files or potentially unwanted software, or looks at specific file types, as I mentioned before. You could tune these classifiers further based on your target customer. Is that enterprise environment or consumer environment? We see that the telemetry between these two differ significantly, so it makes sense to have different classifiers for these and see how they perform. You could also have classifiers that are organization-specific. OK, so we talked about all this diversity. But what's the best way to check if my features are indeed diverse or not? How do I check that? One of the very commonly used techniques is what's called a Pearson correlation matrix. So this technique basically looks at all your feature inputs and gives you a matrix, as you see. The numbers here are basically the correlation metric against each feature. The diagonal yellow line here basically shows how each feature interacts with itself. You can see the value here is 1, which means that it is highly correlated with each other. For the purposes of stack classifier, this is bad, because this basically means that the inputs are very similar, and they don't have anything unique or anything diverse to provide. What you want to focus on is the blue boxes right there, where these features are very diverse from each other. So when we use them as input features in the stack classifier, they again have something very unique to provide in the detection. We have a lot of topics to cover. Before we jump on to our second big topic, let's take a quick AI break. Holly, what do you think is your best AI pun from this?
I think my favorite pun is, why don't neural nets mind the cold weather? Because they can just put on more layers. I love these puns.
I love the audience. All right, so let's dive into how do we develop the stack models. We already have the diverse features. How do we combine these features in an optimal way so that they can represent features to the stack classifier? One of the options is to do Boolean stacking, where you use hard-coded Boolean features from the base learners as your input feature to the stack classifier. Based on our experiments, we find that this is not so optimal. We found that the stack classifier was not able to do better than some of our base learners. We also found evidence of the stack classifier being overfit. The alternate approach of linear stacking works better for our scenario. In this case, instead of using the Boolean labels, you're basically replacing it with continuous values, which is basically nothing but the model probabilities. And what we find is the stack classifier here indeed outperforms some of our single top best classifiers, and there were no results of overfitting here. OK, we know that linear stacking works best, but what sort of model do we use? We do have to answer this question, right? What sort of model would we use to make sense? Now, literature suggests that for stack classification, linear classifiers like logistic regression does really good. Well, when we run our benchmark experiments, we see different results. Before I get into that, let me give you a quick overview of our experiment design. We take n days of our daily incoming telemetry. We use 60% of our oldest data as our train set, the more recent 20% as our validation set, and the most recent unused data as our test set. The train data is used to train the model using supervised training. We then tweak the trained model using our validation set, and then all our benchmark results are on the evaluation set, which is never seen before, most recent data. So the idea of this is to simulate real-world scenario. When we run our experiments, we try a combination of different learners. We try linear learners, boosted learners, and DNNs as well. What we see is LightGBM does the best. And no, we are not trying to promote LightGBM if you were here in the previous presentation. It just happens to do well in both the scenarios. You can see that even at a low false positive rate, LightGBM does better. The red line that you see, that's logistic regression. And you can see it's not doing so well in our case. So we use this classifier. We train our stack classifier. And then we try to measure how the stack classifier does as compared to some of our top individual base learners. And clearly, the stack classifier has some value to provide here. It's canceling out on noise and increasing generalization performance in this case. So to quickly recap the approach, we talked about having or generating very diverse set of classifiers as inputs to the stack classifier. We talked about using model probabilities as input features to train the stack classifier. We saw that LightGBM gives us the best results when we use it to train the stack classifier. And then we use the ROC curve to plot the performance of the stack classifier versus some of our individual top base classifiers. OK, so everything looks good, right? Why not we deploy this in the test, in our real-world data? So often, models tend to do really good in a test scenario. But when you actually deploy this in real world, the performance can vary. The same happened to us. When we use this model to evaluate against 60 minutes of live real-world data, our performance dropped. It dropped from 92% positive recall all the way to 9% positive recall. and our precision dropped from 97% to 13%. Wow, that was astonishing. We further dove into debugging the model. What would have caused this? The first case that we found was data leaks, where information from the target label inadvertently works its way into the training features. To be more specific, we found that some of our detonation-based models indirectly contributed to our target labels. So that caused an overly optimistic assessment of our stack classifiers. Rather than removing those detonation models, we decided why not filter out the instances that directly, that have a good correlation between detonation models and the labels. When we run this, we do observe a 10% drop in recall, but this also helps us prove that the detonation models did have something unique to provide, and keeping those features made sense. The second challenge that we had to deal with was handling missing values, where, as you can see, not all classifiers give out a verdict. In this case, on the right, you'd see that only 2 classifiers have a very low probability of the file being malware, which is basically saying that the file is clean. You would assume that if the stack classifier is training on this data, it would also give out somewhere of a low probability of the file being malware. But no. The stack classifier actually gave a very high probability of the file being malware, a probability of 0.92. We found that the stack classifier was overfitting on this sparse data representation. Now, typically in machine learning, to avoid such situations, you basically remove instances that have more than X% missing values. But remember, a lot of our classifiers are specifically trained to handle special scenarios. So this is kind of expected. And instead of removing those instances, we actually need them to extract the value from them. Oops, this came out late. But what you could do instead is, instead of removing the instance, retain them, but add a Boolean feature indicating which classifiers actually return the value, and then you do a cross-join between different features. The idea behind this is that the learner would try to understand that, hey, if classifier A is missing and then the value is missing, I should not consider that to give out my final verdict and not overfit on that sparse data set. And this helped us work towards it. One more tweak that we did to our models is add a bunch of unsupervised features. Since our data set is very rich, unsupervised learning helped us segregate malware into different threat families or different classes of threats. In this case, we used k-means, and then we used the distance from each of the instance to the centroid of each of the clusters as input features to the stack classifier. And this gave us a further boost in our recall rate, whereas keeping the false positive rate very similar. OK, a quick test. Can you guys tell me what this is? Is no one paying attention? I'll give you a quick hint. This is, the x-axis is based on time. So this is our daily data telemetry that we receive. You can see that on one day, we could have a spike in malware classes. The other day, we could see a spike in clean files. And the third day, we could see a spike in some specialized malware. The point I'm trying to make is the data distribution is highly volatile. This basically contributes to the label distribution being highly volatile. And that results in a very unreliable performance of the stack classifier. Moreover, if we leave this scenario and we don't add any gating to it, this could leave us vulnerable to adversarial attacks if the adversaries figure out how to tamper with our telemetry. So we add some gates to our training data of the stack classifier. We control the total number of training samples using smart sampling. We also control the overall label distribution, the overall ratio of clean to malware ratio that the classifier trains on. And then we also do a continuous monitoring of our incoming telemetry to catch any anomalies or outliers before they get into training. One more AI break. Holly, if you could do the honors.
All right, you ready for another joke? All right, so what do you call a model that goes to the gym too much? Overfit, that's right. Nice. All right.
All right.
Awake now? Good.
So more interesting scenarios. Let's talk about how do we attack some of these class classifiers and how do they perform when they are under attack. So in this case, we craft our own adversarial attacks. Let's consider a scenario where you have a PE file, which is featureized in its binary feature vector. This is given to a model to give out a verdict. And the model says that, hey, I think this is malware. Now we attack this binary feature vector using JSMA, which is Jacobian-based saliency feature mapping. And we perturb the input feature in a way that the same classifier now gives out a clean verdict for the same file. Moreover, to make it more interesting, we do this to two of our top classifiers. We basically flip their verdicts. So whenever the two classifiers say it's malware, we flip it to clean. And when they say it's clean, we flip it to malware. We wanted to see that, hey, in real time, if the attackers are able to basically corrupt our classifiers, how well would the stack classifier handle it? We see that even if we perturb 100% of the samples, the model performance decreases by 30%. This is the recall rate. Now, you might say that 30% is actually quite a lot. But one more thing to notice is this performance is at a fixed 1% false positive rate. Let's take a look at scenario 2, where an attacker injects random features, and these random features somehow get into our telemetry, and we use that to train our stack classifier. So in this case, we basically add rogue classifiers that give out very random values from 0 to 1, and then we use these as inputs to train our stack classifier. Moreover, we add 10 rogue classifiers in the input to see how bad does the stack classifier perform when it is used to train using these noisy inputs. And we can see that the stack classifier clearly identifies that, hey, all of these 10 classifiers are noisy, and I don't want to train on it because it is completely random. When you look at the actual evaluation, you can see that when I have no random classifiers to 10 classifiers, my false positive increases by just 0.4%. And then my true positive decreases from 96.1 to 95.8. Not that bad. OK, let's consider one more scenario where the attacker is just highly motivated to break our ensemble approach in ways we don't see coming. We have other mitigations across the machine learning attack surface to prevent this from happening. From a samples perspective, we control the overall number of instances that we use for training to prevent any flooding of incoming telemetry. We control our label distribution as well as the sources where those labels come from. From a feature perspective, we update our features regularly, and we constantly check for feature evasion. And then we also add unsupervised features to make up for human bias in the classifiers. Once the model is developed, we have specific requirements that the model has to pass. If it does not, then we do not ship that model to production and retain the original model that is already deployed. And once the model has been deployed to either the client or the cloud, we continuously monitor the behavior or the performance of this model. We look at the overall block ratios, and we also look at any anomalies that we might see in the overall block ratio.
All right. So let's talk about real-world results. So as Jugal showed, the experimentation seemed to indicate that the ensemble approach would give us a really nice boost above and beyond our base classifiers. And in fact, it did. So you don't often see this kind of results that mimic what you saw in experimental mode so well, but this has given us a really nice boost. On any given month, the ensemble models are giving us anywhere from 10 to 15% more detections than we were originally getting from our cloud protection system. And that's a hefty chunk. That represents a large number of additional customers being protected. And about 75% of the threats our customers encounter are related to executable files. And the ensemble models are doing really well against them. But it's protecting against thousands of other file types. Many of them we don't even have specialized classifiers for. So it has really given us a nice boost above and beyond our base level detection. An unexpected benefit that we got out of this is interpretability. So if you think about some of those models that Jugal was showing you earlier, some of them have millions of features. And when you're trying to troubleshoot why a model gave you the wrong decision on something, dealing with hundreds of thousands or millions of features makes it virtually impossible. So the nice thing about the Ensemble model is that it's a pretty limited feature set. You're just using the probability scores of the other models, and it's pretty simple to see what's contributing to the Ensemble's decision. The other benefit that we got out of this is that we can take a subset of threats. So let's say we have a specially trained JavaScript model. We can compare the results of that model to what the Ensemble is doing and find gaps, right? So if the JavaScript model is only detecting 20% of the files that the Ensemble model is detecting, well, maybe there's a problem with that base model. And thank goodness the Ensemble model is picking up the slack. But what can we do to go tune that base model to make it stronger, to give better signals overall? So it's had a lot of unexpected benefits that were pretty awesome. So just to recap really quickly why you might want to consider an Ensemble approach. Really great at filtering out noisy signals. So if you've got a model that's kind of doing well and then not doing so well, or maybe there's something going on with its training that's causing it to misbehave, the Ensemble is really nice at smoothing out those predictions and making sure that they remain pretty accurate and resisting the that fluctuation that could, if you're only using the base models, could cause you to miss some attacks. Definitely increased our predictive power. We saw a huge boost in our detections, and the nice side benefit of that is that we had great interpretability for not only our current models, but it's really easy to interpret the stack classifier as well. And of course, last but not least, adding resilience against adversarial attacks, right? I'd like to show you how these ensembles have protected our customers in some real-world scenarios. So again, this is focusing on the first two layers, client-based protection and the metadata-based cloud layer. This first case study, it's interesting not because it was this huge, large-scale attack. It's actually very interesting because it was tiny. This affected less than 100 people, mostly centered in Canada. And most of the targets were small to medium businesses. So this was a targeted, specialized attack that was picked up by our Ensemble model. So the way this started out was an email. It looked like this email came from a landscaping supply company. We've obfuscated the name here, but it was a local landscaping company in Canada. And so it said, hey, I've got an invoice here for you, and attached this PDF file. So when you open this PDF file, if you weren't one of our customers, you would see this DocuSign-looking file. And it's got a link in it to view the actual DocuSign agreement. And that link would take that customer to a phishing site, which would then try to steal their credentials. Luckily, Ensemble model kicked in and helped us out here. So how did this work in practice? The local machine learning models flagged this PDF file as suspicious. So extracted the properties from the PDF file, sent all those properties up to our cloud-based system where all of our models ran on that metadata. As you can see at the very top, our PDF classifier did not respond. Luckily, the Ensemble model looked at the other model results and saw that those low-level signals were similar to other attacks that it had trained on and knew that this was a malicious PDF file. So within milliseconds, it sent that block response back up to our cloud, back to the client, and prevented that PDF file from even being open, saving that person from even clicking the link to go to that phishing site. This second attack was of a larger scale, but it's really interesting because it was about 3,000 customers in Brazil, and every single attack was different. It was the same campaign. It was this heavily obfuscated JavaScript file, but every single one of them was different, so super polymorphic, okay? Again, this started out from an email. Email contained a zip file that looked like a document. When you open the document, it contained a VBS file that kind of looked like a document. If the person opened that VBS file, that would install a Chrome extension. And none of these particular components were the payload. The payload was actually this obfuscated JavaScript file that the Chrome extension downloaded. You can see in the unobfuscated version down there what it was trying to do, steal their credit card credentials and other things. So we call this Bangos. Luckily, this was pretty similar to the other example I showed to you. So we had great low-level signals from our local machine learning model. It said, hey, this JavaScript file here looks suspicious. I'm going to send the metadata up to cloud. The cloud ran all of the different models, and we came close with the JavaScript model, so it was a little more than 50% confident that this was malware, but not confident enough to block. Luckily, the Ensemble had learned that this combination of signals means that this file is actually malware. And so within milliseconds, it sent that signal back to the client and told the client to block, and the customer, this JavaScript file wasn't allowed to execute, wasn't allowed to steal the customer credentials. All right, just a few last words. Huge thanks to all of the people who contributed to the research we have done here, building the Ensemble model. This kind of thing really takes a village, so Jugal and I have the privilege of being able to talk to you about what we learned, but there were a ton of people who put a lot of work into this. There's even names that would not have fit on this slide. A couple of references. There is a blog post that talks about that Brazil attack in detail and some other information about the Ensemble work we did here. If you're going to Virus Bulletin next week, make sure you catch Joe and Karishma's talk. They're going to be covering a subject that is in the same vein as what we spoke about today. Just the most important takeaways I want you to have before you walk out of here. When you're thinking about client-based protection, make sure you don't put all of your eggs in the client basket, because it's really easy to evade, really easy to test, super easy for an adversary to gain the system and figure out your answers. If you're considering an Ensemble approach, you need to make sure you have a great, diverse set of base-level classifiers to begin with. Use the Pearson correlation model or some of the other techniques that Jugal talked about before you start to add an Ensemble layer on top of it. Once you think you've got a really strong set of classifiers, test it. Try out some attacks. See if you can get past your defenses. And if you can, go back to the drawing board. Maybe your diverse set wasn't as diverse as you thought, or you need to add some bolstering somewhere else, all right? Then after you've deployed, set up checkpoints, set up monitors, make sure that every single part in the pipeline of your machine learning system has some guardrails to prevent people from tampering with your system, or at least try to prevent. Right. And I think we have maybe 2-3 minutes for questions. Okay.
Yep. We've got one over here. We've got mic runners on both sides, so just raise your hand and we'll come to you.
So just summarize what you just said on the high level. You have a lot of classifiers, and you're suggesting one master ensemble layer irrespective of the file type, right?
We actually allow the base classifiers to give their answer. So if a base classifier says block, we block. And we allow the Ensemble to take the low-level signals and also say block in cases where they don't.
Right. So my follow-up question is, have you tried for different file types to have different ensemble layers, and did that change the performance?
We have ensembles for portable executables and ensembles for non-PE. And we may look at other slices of that, maybe tailored to geographies or customer sets or files. You know, there's other ways where you might deploy it, yeah.
I'd say segregating it based on the file type does add an advantage, so I would recommend that.
Okay, we've got one over there.
Hi, thanks for the talk, awesome. Just to know, how do you protect yourself from getting like so many data corrupting your training? Because that's not clear. Because I could just build a distributed attack to do the same trick as the calculator is a malware.
That's a great question, and I don't think anyone should ever assume that their data is totally clean, right? And I think the great thing we saw with the Ensemble model is that it can help filter out some of that noise. And if you have a strong classifier, it should be resilient to some of that noise. I don't know, Jugal, if you have a different perspective.
No, I understand. I mean, I agree with you, totally agree with you. Even when you're developing a stacked ensemble, the first thing you want to do is look at the data. What sort of story your data says, identify data leaks, identify how many of them have missing values, and then develop a strategy on how do you want to tackle the problem, if that makes sense.
Thanks.
Sure.
Yeah, maybe one more. Oh.
Oh yeah, just to kind of like clarify, for the base classifiers, do you split your training data into different subsets or use the same data for all the classifiers?
So the training data is also part of the diversity. So you have classifiers that operate on different data sets, not just subsets, but a completely different class of data set.
Okay, thanks.
Sure.
Okay, we got
I
really
have
one
question.
more.
So whenever you find a new threat that you have not seen before and that you have not, do you retrain your models? How do you do that? Like, this is just on the set of known entities, but what about something unknown and then you found out? Do you retrain your models?
Some of them train multiple times a day. It depends on the models. Some train multiple times a day, some train daily, some have a slower cadence. So yes, the answer is as soon as we have new labels on things, then they go back to train the models.
Okay. And the second question was, do you use this for Azure Edge? I mean, this is just PCs, but what about Azure? Do you plan to, or can this be used for Azure Edge endpoints? You know what I mean?
So we work really closely with the Azure ATP team and the Office ATP team, and we've shared the Ensemble work that we have done with them. I'm not sure if they've incorporated this specifically into their protection capabilities, but we share all the stuff we do here with those two teams.
So the determinations that we set using the stacked ensemble are all of our arsenal of base classifiers. They are being shared across the company. So.
Thanks.
All right. Let's give Holly and Jugal a big round of applause. Thank you.